We look up at the sky during the day, and we see a tyrant, the sun. It dominates the heavens, a singular blinding disk of gold that banishes all other lights. It sits alone in the center of our solar system, holding court over the planets, the asteroids, and the comets. To our eyes, the sun is a solitary creature, a king without a court, reigning in splendid isolation over a kingdom of empty space. But this isolation is an illusion of time. The sun was not always lonely. If we could wind the cosmic clock backward, past the age of the dinosaurs, past the formation of the Earth, back 4.5 billion years, we would find a very different scene. We would find that our sun was born into a crowded, chaotic, and beautiful family. It was one of a litter, 1,000 brothers and sisters born from the same cloud at the same time, igniting together in the dark. To find the family, we must first find the womb. Space is not truly empty. It is filled with the interstellar medium, a thin soup of gas and dust, mostly hydrogen, with a sprinkling of heavier elements left behind by dead stars. Usually, this medium is thin and hot, but in certain pockets of the galaxy, the gas collects. It pools in the gravitational valleys of the spiral arms. It cools down. It becomes a giant molecular cloud. These structures are so vast that it takes light 100 years to cross them. They are mountain ranges of gas, floating in the void. From the outside, they appear pitch black, so dense with dust that they block the light of the stars behind them, appearing as silhouettes against the star field. Inside, they are incredibly cold, only 10 degrees above absolute zero. This cold is essential. Heat is energy. Heat makes gas molecules move fast and push apart. Cold makes them slow down and clump together. Deep in this freezing dark, 4.6 billion years ago, a pre-solar nebula began to stir. Perhaps it was triggered by the spiral arm of the galaxy sweeping through, or perhaps by the shock wave of a nearby supernova slamming into the side of the dark cloud. Gravity woke up. Once a clump of gas gets dense enough, gravity wins the battle against pressure. It pulls more gas in, the clump gets heavier. It pulls harder. It is a runaway process known as gravitational collapse. But a giant molecular cloud does not collapse into a single star. It is too big for that. It contains enough mass to make thousands of suns. So, it fragments. The cloud breaks into pieces, and those pieces break into smaller pieces, like a pane of glass shattering in slow motion. Each shard of glass is a protostellar core. In the darkness, thousands of these cores began to shrink simultaneously. As they shrank, they spun faster. They flattened into disks. And in the center of each disk, the friction of falling gas turned into heat. One by one, the lights turned on. Fusion began. The sun ignited. But it did not ignite alone. If one were to stand on a rocky asteroid in that early solar system and look up, the sky would not be the black, empty expanse we see today. It would be a jewelry box. The sky was ablaze with nearby stars. Some were massive blue giants, burning furiously bright. Some were yellow stars, twins of the sun, and thousands were dim, red dwarfs. They were packed tight. In our neighborhood today, the nearest star is 4 light years away, but in the birth cluster, the stars were perhaps only a few light weeks apart. It was a cosmic creche, a nursery where the sun was just one face in the crowd. We can still see clusters like this in the sky today, such as the Pleiades, the 7 sisters. They are a family of siblings that haven't drifted apart yet, still holding hands in the dark. But childhood in the cosmos ends. The force that creates the cluster, gravity, is fighting against the energy of the stars themselves. The massive blue stars in the family were violent. They emitted intense ultraviolet radiation and eventually exploded as supernovae. These explosions acted like great cosmic winds, blowing away the remaining gas of the molecular cloud. This was the critical moment. The gas provided much of the gravity holding the cluster together. When the gas was blown away, the total mass of the system dropped, and the gravity became too weak to bind the stars. The cluster became unbound. The siblings began to drift. It wasn't an explosion, but a slow, gentle dissolution. Like a dandelion head blowing in the wind, the seeds floated away one by one. The sun began its long journey, drifting out of the nursery and into the wider stream of the Milky Way. The galaxy is a rotating disk, but it pulls at different speeds. The inner parts move faster than the outer parts. This shearing force acted like a grinder, pulling the cluster apart. A sibling slightly closer to the galactic center raced ahead. A sibling slightly further out fell behind. Over one orbit of the galaxy, a galactic year, the family was stretched into a long stream. Over 20 orbits, the family was scattered completely, mixed into the general population of the Milky Way. This is why the sun looks lonely today. We are separated from our kin by thousands of light years. We have orbited the galaxy 20 times since we last saw them. But the drifting apart is natural. It is the way of the galaxy. The vast spaces between the stars are not signs of abandonment. They are signs of growth. We needed to leave the nest to build the solar system, to build the Earth. We could not have survived in the crowded cluster. The radiation was too high. The environment too chaotic. We needed the quiet of the open arm. And so we find ourselves here, safe, stable, solitary. The frenetic energy of the nursery has been replaced by the calm stability of the open void. The sun has found a quiet corner of the galaxy to raise its planets. Now, as the story pauses, let the feeling of that solitude settle over you. The immense distance between the stars is a buffer. It is a blanket of silence that protects us. The sun is resting in its own private space, and so are you. The chaos of the crowd is far behind. The noise of the siblings has faded into the background hum of the galaxy. There is only the steady, golden light and the peaceful dark that surrounds it. Drift in the quiet of the solar system. Safe in the vastness. Sleep. We have watched the family scatter. We have seen the great cluster of 1,000 stars, the nursery where our sun was born, slowly dissolve into the streams of the Milky Way. Like dandelion seeds caught in a gentle breeze, the siblings drifted apart, carried by the rotation of the galaxy into the vast, anonymous dark. For 4.5 billion years, the sun has traveled alone. It has circled the galactic center 20 times, moving further and further from its kin with every revolution. Today, the stars that shared our birth cloud are lost in the crowd. They are hidden among the 100 billion other stars that make up the disk of our galaxy. To the naked eye, they are indistinguishable from strangers. But they are not gone, and they are not unrecognizable. Nature, it seems, keeps a meticulous record of origins. Every star carries a secret identity card, stamped into its very substance, a chemical fingerprint that tells the story of where it came from and who its family is. Tonight, we become detectives. We will learn how to read the rainbow. we will discover that the light streaming from the distant stars is not just illumination, it is information. We will hunt for the solar siblings, hidden in the night sky, and we will find that even across the unimaginable distances of space, the bond of blood, or rather the bond of gas, can never be truly broken. To find a needle in a haystack, you must first know exactly what the needle looks like. To find a sibling of the sun, we must first understand the sun itself. We tend to think of stars as simple balls of fire, but they are complex cauldrons of chemistry. The cloud from which the sun formed, the solar nebula, was not just pure hydrogen and helium. It was a specific recipe. It had been seasoned by the generations of stars that died before it. Imagine a soup. Every pot of soup is slightly different. One might have a pinch more salt. Another might have a dash of pepper. The solar nebula had its own unique flavor. It had a specific amount of iron, a specific amount of magnesium, a specific ratio of carbon to oxygen. This mix was determined by the specific supernovae that exploded near our nursery 4 billion years ago. When the cluster formed, every single star in that family inherited the same mix. The sun, its big brothers, and its little sisters were all made from the same batch of dough. This is the key. While the stars have moved apart, their chemistry has remained frozen in time. The iron that is in the sun today is the same iron that was there at the beginning. If we can find another star out there with the exact same chemical ratio as the sun, we have found a sibling. But how do we taste a star? We cannot go there. We cannot take a sample. We have only one thing to work with: light. Enter the art of spectroscopy. When we pass sunlight through a prism, it spreads out into a beautiful rainbow: red, orange, yellow, green, blue, indigo, violet. But if you look closely at this rainbow with a high-powered instrument, you will see something strange. The rainbow is not perfect. It is full of holes. There are thousands of thin, dark lines cutting across the colors. These are the Fraunhofer lines, named after the German optician who mapped them in the 19th century. These lines are the shadows of atoms. As light leaves the core of the sun and passes through the cooler outer atmosphere, the atoms in that atmosphere absorb specific wavelengths of light. Iron absorbs a specific shade of blue. Calcium absorbs a specific shade of violet. Sodium absorbs a specific shade of yellow. The resulting pattern of dark lines is a barcode. It is a unique readout of exactly what elements are present in the star and in what quantities. Every star has a barcode, and for most stars the barcode is different. Some are metal-poor, born in the early universe. Some are metal-rich, born in dusty environments. So, the hunt begins. We are looking for a star with a barcode that matches the sun's perfectly. But the haystack is enormous. The Milky Way contains billions of stars. Scanning them all is a task beyond human capability. We need a machine. We need Gaia. Gaia is a space telescope launched by the European Space Agency. It is currently orbiting out in the deep quiet far beyond the moon. Its mission is to make the most precise map of the galaxy ever attempted. Gaia does not just look at where stars are. It looks at how they move. It measures their positions, their distances, and their velocities with mind-bending accuracy. This allows astronomers to play the movie backward. If we know where a star is now, and we know how fast it is moving, we can calculate where it was 1 million years ago, and 1 billion years ago. We are looking for stars that retrace their steps back to the same patch of sky where the sun was born. We are looking for paths that intersect in the past. In 2014, a team of astronomers led by Ivan Ramirez combined the chemical data with the orbital data. They started with a list of 100,000 potential candidates. They filtered them. First, they threw out the stars that were too young or too old. The sibling must be the same age as the Sun, 4.6 billion years. Then they threw out the stars with the wrong chemistry. Too much iron? Gone. Too little oxygen? Gone. The list shrank from thousands to hundreds, from hundreds to dozens, and then finally they found a match. A star with the unromantic name of HD 162826. Let us travel to this star. It is located in the constellation of Hercules, the strong man. It is about 110 light-years away from Earth, close enough to be seen with binoculars, but too faint for the naked eye. If you could fly a spaceship to HD 162826, you would feel a strange sense of déjà vu. It is a yellow star, spectral type F. It is slightly hotter than the Sun and slightly more massive, about 15% bigger. It is a big brother. But the light it emits feels familiar. It has the same golden hue. Spectroscopically, it is a twin. The barcode of iron, element by element, lines up almost perfectly with the Sun. It is overwhelmingly likely that this star formed in the same molecular cloud as we did. Imagine the history. 4.5 billion years ago, the Sun and HD 162826 were neighbors. They might have been only a few light weeks apart. They shared the same view of the nebular nursery. They felt the same shock waves from the nearby supernova. Perhaps in the chaos of the early cluster, they even exchanged materials. And then they drifted. For eons, they have traveled separate paths through the galaxy, encountering different spiral arms, dodging different nebulae, and now they are passing each other again, or at least they are in the same quadrant of the galaxy. Finding HD 162826 changed our perspective. It proved that the search is possible. It proved that the family is out there. But it is just one. There were 1,000. Where are the others? Some are likely on the other side of the galaxy, hidden behind the dust of the galactic core. We may never see them. Some may have died. The massive blue siblings exploded long ago. We might be able to find their remnants, neutron stars or black holes drifting in the dark, but checking their DNA is impossible. The explosion erased the fingerprint. But many of the red dwarfs, the little sisters, must still be alive. Red dwarfs are dim. They are hard to see even when they are close. It is very likely that there are solar siblings much closer to us than HD 162826, hiding in plain sight as faint red dots. We just haven't pointed the spectrograph at them yet. Let us contemplate the emotional resonance of this connection. We often feel that the universe is cold and indifferent, that we are an accident of chemistry on a lonely rock. But the story of the solar siblings tells us that we are part of a generation. We belong to a cohort. There is something comforting in looking up at the constellation Hercules through a pair of binoculars and knowing that one is kin. It makes the night sky feel less like a void and more like a neighborhood. Imagine if HD 162826 has planets. Astronomers have looked, but so far they haven't found any massive gas giants orbiting it. But that doesn't mean there are no Earths. Small, rocky planets are hard to detect. What if there is a world there? a world bathed in the same golden light as ours, a world made of the exact same mix of elements. If life arose there, it would be our cosmic cousin. It would be built from the same stardust recipe. As you lie in the dark, think about your own chemical composition. The iron in your blood, and the calcium in your bones, the carbon in your cells. These atoms were not made on Earth. They were gathered in that dark molecular cloud. You are a sample of the solar nebula. You carry the barcode of the family. In a sense, you are related to that distant star in Hercules. Let the concept of DNA expand. Usually we think of DNA as biological, the double helix, but there is also stellar DNA, the spectrum of light. Both carry information across time. Both tell us where we came from. The light entering your window tonight is carrying messages. Most of the stars you see are strangers. Their light is blue, or red, or white. Their chemistry is different, but hidden among them are the ones that match. The search continues. The Gaia telescope is still gathering data. New candidates are being added to the list. Perhaps one day we will find a sibling that is truly close, a twin sun just a few light years away. But for now, the knowledge is enough. We are not orphans, we are just travelers. We have ventured far from the nest, but the nest is still in us. Let your mind drift back to the image of the prism, pitch 1%, the rainbow of light, the dark lines. It is a code, a language. The universe is speaking to us in color. I'm here, the star says. I'm like you. Let that sense of recognition wash over you. The immense distances of space cannot erase the connection. 110 light years is nothing to a beam of light. It is a mere century of travel. The light from our sibling arrives here, passes through our atmosphere, and lands on our retinas or our telescopes. It is a handshake across the void. In the next chapter, we will look closer at the possibility of life. We will ask the question, panspermia. Did life start on Earth, or did it start in the cluster? Could rocks exchanged between the siblings have carried the seeds of biology? We will explore the idea that perhaps we are not just related to the stars, but related to the life that might orbit them. But for now, stay with the light. Stay with the golden glow of the brother star. It is shining steadily in the constellation of the strong man. It remembers the cloud. It remembers the beginning. You are part of a great, scattered family of light. Rest in that belonging. Sleep in the spectrum. Sleep. We have established that the sun was born into a large and boisterous family. We have traced the chemical fingerprints that link us to stars now scattered across the breadth of the Milky Way, identifying them as our long-lost siblings. But family is more than just shared DNA or, in this case, shared stellar chemistry. Family is also defined by proximity, by interaction, and by the exchange of gifts. In the human world, siblings share toys, germs, and stories. In the stellar world, the siblings of the sun shared something far more substantial. They shared the building blocks of their own systems. They traded comets, asteroids, and perhaps the very seeds of life itself. To understand this great cosmic exchange, we must reconstruct the geography of the birth cluster. As we drift back in time 4.5 billion years, we find that the architecture of the solar system was not the neat, orderly, clockwork mechanism we observe today. It was a place of violent transformation. The planets were migrating, shifting their orbits in a chaotic dance. The space between the planets was filled with the debris of creation, trillions of icy rocks and stony asteroids that had not yet been swept up or ejected. This was the era of the heavy bombardment. In the modern solar system, an asteroid impact is a rare and catastrophic event, but in the early days, it was the status quo. The Earth, the Moon, and Mars were pummeled relentlessly by rocks raining down from the sky. These impacts were violent, yes, but they were also generative. When a massive asteroid strikes a planet, it does not just bury itself in the crust. It blasts a fountain of debris upward. If the impact is energetic enough, rocks are flung with such velocity that they overcome the gravitational pull of the planet. They escape into space. They become travelers. We know this happens because we have found pieces of Mars right here on Earth. Meteorites that were blasted off the red planet millions of years ago drifted through the void and eventually landed in Antarctica or the Sahara. But in the crowded environment of the birth cluster, the journey of an ejected rock would have been very different. Today, if a rock escapes Earth, it is likely to stay within the solar system, perhaps eventually hitting Jupiter or the Sun, or drifting endlessly in the vacuum. The distance to the next star, 4 light years, is simply too vast to cross by chance. However, inside the cluster, the nearest star was not 4 light years away. It was perhaps only a few light weeks away. The solar system was rubbing shoulders with its neighbors. The gravitational boundaries were porous. A rock blasted off the surface of the early Earth, or early Mars or Venus, would not have to travel through an endless void to find a new home. It would only have to drift a relatively short distance before being captured by the gravity of a sister star. This theoretical mechanism is known as Lithopanspermia, the transport of life, or the precursors of life, via stones. It paints a startling picture of the early cluster. We can imagine the family of stars not as isolated islands, but as an archipelago connected by a constant traffic of debris. Millions of tons of rock and ice were likely traded between the siblings. The early Earth was not a closed system. It was part of an open network. The most numerous travelers were not rocks from the inner planets, but comets from the outer edges. Every star in the cluster was forming its own Oort cloud, a vast, spherical shell of icy bodies surrounding the system. In the cramped quarters of the nursery, these clouds would have overlapped. The outer edges of the Sun's domain would have brushed against the outer edges of HD 162826's domain. As the stars moved past one another in their slow gravitational waltz, they would have perturbed these clouds. A close pass by a sibling would have sent a shower of comets plunging inward toward the Sun, but it would also have stripped comets away, stealing them. Mathematical models suggest that a significant fraction of the comets in our own Oort cloud, perhaps even the comets that brought water to the early Earth, were not formed by the Sun at all. They were adopted. They were formed around one of our siblings and then captured by the Sun during a close encounter. This implies that the water in our oceans, the very medium of life, might be a communal resource. It is a blend of ices gathered from across the entire family. We are swimming in a liquid heritage that belongs to the cluster, not just to the star. But the implications go deeper than water. We must consider the timing of biology. The fossil record on Earth suggests that life began remarkably early. Almost as soon as the planet cooled enough for liquid water to exist, life appeared. Some evidence points to biogenesis occurring as far back as 4.1 or even 4.2 billion years ago. This overlaps with the time the Sun was still embedded in, or just leaving, its birth cluster. If simple microbial life existed on Earth during this time, it is statistically probable that rocks containing these microbes were blasted into space by impacts. In the deep freeze of space, bacteria and spores can survive for long periods in a state of suspended animation. Encased in rock, shielded from UV radiation, they are remarkably resilient. If such a rock drifted across the short gap to a sibling star and landed on a primitive planet there, it could have seeded that world with life. Conversely, life might not have started here. It is possible that life began on a planet orbiting one of our faster evolving siblings, perhaps a massive star that cooled its protoplanetary disk more quickly. A rock from that system could have traveled to the young Earth, falling as a meteorite into the warm, prebiotic oceans, delivering the first spark of biological complexity. We might be the colonists. This concept fundamentally reframes our search for extraterrestrial life. When we look for the solar siblings, we are not just looking for stars that resemble the Sun. We are looking for the places where our biological cousins might reside. If Lithopanspermia occurred, then life in the Milky Way might not be a series of isolated, independent genesis events. It might be a single tree of life, rooted in this one specific cluster, its branches now scattered across the galaxy. The search for these siblings is also a search for the conditions that make a planetary system habitable. Not all siblings are created equal. Some stars in the cluster would have been subjected to intense radiation from the massive giants nearby, stripping away their planet-forming disks before they could build an Earth. Others might have been ejected from the cluster too violently, disrupting their orbits. But the Sun seems to have been one of the lucky ones. We stayed in the cluster long enough to be enriched by the supernova, receiving the iron and radioactive elements that heat our planet's core. But we left before the environment became too destructive. We walked the fine line between enrichment and annihilation. Finding other stars that walked this same line is a priority for astrobiologists. There is a specific type of star we are hunting for: the solar twin, a sibling that is not just genetically related, but physically identical to the Sun in mass, temperature, and luminosity. If we find a solar twin that was born in the same cloud, it represents the most perfect control group for the experiment of life. If we look at that star and find planets, but no life, it tells us that life is rare and difficult. But if we find biosignatures there, oxygen in the atmosphere, the spectral edge of chlorophyll, it would be a discovery of unparalleled magnitude. It would suggest that the galaxy is teeming with our relatives. The mechanism of the drift that separated us is also a crucial part of the story. As the gas of the birth cluster dissipated, the gravitational glue vanished. The stars were released into the galactic stream. But this release was not uniform. The galaxy is filled with resonances, gravitational bumps and grooves created by the spiral arms and the central bar. These resonances act like sorting machines. As the siblings drifted, some were caught in resonances that pushed them inward toward the galactic core. Others were pushed outward toward the rim. The Sun is currently located about 26,000 light-years from the center, in what is often called the galactic habitable zone, not too crowded with dangerous radiation, but not too sparse to lack heavy elements. It is possible that the Sun has migrated significantly from its birth position. We might have been born much closer to the center and migrated outward, carrying our planetary system with us like a raft on a river. By finding our siblings and mapping their current positions, we can reverse engineer the migration. We can reconstruct the path of the Sun through the galaxy. We can build a travelogue of our solar system's journey through the Milky Way. This reconstruction is difficult because the galaxy is a dynamic, churning place. Stars do not stay put. They bob up and down through the galactic plane like horses on a carousel. They are scattered by passing molecular clouds. The family has been stirred into the batter of the galaxy so thoroughly that retrieving the original pattern requires computing power that has only become available in the last decade. But the picture is becoming clearer. We are identifying moving groups, streams of stars that are not bound together by gravity, but which move through the galaxy with the same velocity vector. These are the ghosts of dissolved clusters, the Hercules stream, the Sirius stream, the Castor moving group. The Sun is currently passing through some of these streams, intersecting with other families, but we are looking for our own stream, the solar stream. Imagine a river of stars, invisible to the naked eye but obvious to the data, winding its way through the spiral arms. The Sun is just one droplet in this river. Finding the other droplets will allow us to map the shape of the river and, ultimately, the shape of the cloud from which we fell. The exchange of material in the early days has ceased. The distances are now too great. We are no longer trading comets or rocks with our kin. The solar system is effectively a closed box, quarantined by the vastness of interstellar space. But the legacy of that early open era remains buried in the geology of our planets and the chemistry of our bodies. We are looking for a mirror, a star that reflects our own history. And as we continue to scan the heavens, cataloging the light of millions of suns, the probability of finding that mirror approaches certainty. The family is out there, drifting in the silence, waiting to be recognized. The scattering of the Sun's family was not a singular event, but a process that has continued for the entirety of the solar system's existence. For 4.5 billion years, the Milky Way has been turning. It is a majestic, slow-motion carousel, but it is not a perfect machine. It wobbles, it ripples, it breathes. The stars within it are not fixed to a rigid frame. They are independent travelers, bobbing up and down through the galactic plane, drifting inward toward the core and outward toward the rim. This relentless motion is known as the galactic churn. It is the great mixer of the cosmos. Over 20 orbits around the center, the 1,000 siblings of the Sun have been subjected to the chaotic gravity of spiral arms, the tug of passing molecular clouds, and the influence of the galactic bar. They have been thoroughly reshuffled. To look up at the night sky today is to look at a crowd of strangers, a random assortment of stars brought together by chance for a brief cosmic moment before they drift apart again. Finding the lost family in this churning ocean seems, at first glance, to be an impossible task. It is a search for a needle in a haystack, but the haystack is 100,000 light-years wide and contains at least 200 billion needles. To solve this puzzle, human eyes and traditional telescopes are insufficient. We cannot simply look for stars that look like the Sun. A yellow G-type star is a common object. There are billions of them. We need to look deeper. We need to know not just what a star looks like, but where it has been, how it is moving, and exactly what it is made of. We need a machine capable of mapping the galaxy in 6 dimensions. Enter Gaia. Launched by the European Space Agency, this spacecraft is perhaps the most ambitious mapmaker in human history. Floating in the quiet stability of Lagrange Point 2, a million miles from Earth, Gaia spins slowly, sweeping its twin telescopes across the heavens. Its mission is to chart the positions, distances, and motions of more than 1 billion stars. The precision of this instrument is difficult to comprehend. Gaia can measure the position of a star with an accuracy equivalent to measuring the width of a coin sitting on the surface of the Moon, as seen from Earth. It detects the tiniest shifts in parallax, allowing us to triangulate the distance to stars on the other side of the galaxy. But more importantly for our search, it measures proper motion, the speed and direction of a star as it travels across the sky. With this data, astronomers can perform a feat of chronological alchemy. They can reverse the flow of time by taking the current position and velocity of a star and applying the laws of orbital mechanics. They can calculate where that star was 1,000,000 years ago, and 10 million years ago, and 100 million years ago. They can rewind the tape of the galaxy. The goal is to find intersex. We are looking for stars that, despite being widely separated today, trace their paths back to a single point in space and time, the location of the Sun's birth cluster, 4.6 billion years ago. This is a messy calculation. The galaxy is not a smooth gravitational pool, it is lumpy. We have to account for the gravitational influence of things we cannot see, like dark matter halos and ancient spiral density waves. The further back we go, the fuzzier the picture becomes. But when we combine this orbital rewinding with the chemical fingerprinting we discussed in Chapter 2, the candidates begin to emerge from the noise. We have already met HD 162826, the first sibling identified in the constellation Hercules. But the search did not stop there. In 2018, researchers from the Ambry Project, a massive galactic archaeology survey, announced the discovery of a second, perhaps even more compelling candidate. Its name is HD 1863-2. Located about 184 light-years away in the southern constellation of Pavo, the Peacock, this star is remarkably unassuming. You cannot see it with the naked eye. Through a small telescope, it appears as a faint, steady point of light. But the data tells a profound story. HD 1863-2 is not just a sibling, it is a solar twin. In stellar classification, the Sun is a G2V star. HD 1863-2 is also a G2V star. It has roughly the same mass as the Sun. It has the same surface temperature. It has the same luminosity. And most critically, it is the same age. When we analyze its light, the barcode of absorption lines matches the Sun's even more closely than our previous candidate. The ratios of iron, oxygen, magnesium, and silicon are identical within the margins of error. If you were to stand on a planet orbiting HD 1863-2 and look up at your Sun, it would look exactly like the Sun we see from Earth. The light would have the same warmth, the same golden hue. Plants from Earth would likely be able to photosynthesize there without modification. It is a mirror image of our home star, drifting in the southern sky. The discovery of HD 1863-2 was a triumph of galactic archaeology. It proved that the Sun's family is not lost forever. They are simply hiding in plain sight, waiting for us to develop the tools to recognize them. But it also raises a fascinating question about nature versus nurture in the cosmos. Here, we have two stars, the Sun and HD 186302, born from the same cloud with the same mass and the same chemical composition. They are genetic, identical twins, but they have lived very different lives. The Sun traveled one path through this galaxy, encountering specific spiral arms and molecular clouds. HD 186302 traveled another. Did this difference in journey affect the system that formed around it? We know the Sun has a retinue of 8 planets, including rocky worlds and gas giants. We do not yet know what orbits HD 186302. Astronomers are currently scouring this star for exoplanets. It is a prime target. If we find planets there, we can compare them to our own. Did a similar grand tack migration of Jupiter shape that system? Did it undergo a late, heavy bombardment? If we find a system that looks like ours, it suggests that the formation of the solar system was deterministic, written into the initial conditions of the cloud. If we find a system that is radically different, perhaps with hot Jupiters hugging the star or super-Earths, it suggests that the random events of history play a larger role than the initial genetics. The search for siblings is also complicated by the phenomenon of doppelgangers. The galaxy is a big place, and big molecular clouds are common. It is statistically possible for a star to be born in a completely different part of the galaxy, from a completely different cloud, but to happen to have the same chemical composition as the Sun by pure chance. Nature might have mixed a similar batch of dough in 2 different kitchens. This is why the orbital dynamics are so crucial. A doppelganger might look like a sibling chemically, but its path through the galaxy would be wrong. It would be an imposter. To confirm a true sibling, we need the 6D match: position, velocity, and chemistry. We are looking for the intersection of all these lines of evidence. As Gaia continues to send back data, the catalog of the Milky Way is growing in resolution. We are moving from a blurry sketch to a high-definition photograph. New data releases, DR3 and soon DR4, are refining the proper motions of millions of fainter stars. This opens up the possibility of finding the little sisters, the M-dwarf siblings. Remember that the birth cluster was likely dominated by red dwarfs. For every sun-like star, there were probably 10 or 20 red dwarfs. These stars are dim, making them harder to study spectroscopically. We struggle to get a clean chemical fingerprint from them because they are so faint and their atmospheres are complex, filled with molecules that muddy the spectrum. However, because they are so numerous, they represent the bulk of the missing family. Statistically, the nearest solar sibling to Earth is almost certainly a red dwarf, not a G-type twin like HD 186302. It might be sitting right under our noses, a faint red dot only a few dozen light-years away, catalogued as a random anonymous star. Finding these little sisters is the next frontier. Advances in infrared spectroscopy are beginning to allow us to pierce the veil of their complex atmospheres. If we can identify a cluster of red dwarf siblings, we can learn about the mass function of our birth cluster, the ratio of big stars to small stars. This would tell us a great deal about the density and the violence of the environment in which we were born. The galactic churn that separated us is also the mechanism that allows us to sample the galaxy. If stars never moved, we would only ever know our immediate neighbors. But because the galaxy mixes its population, we have the opportunity to interact with stars from all over the disk. The stars passing near the Sun today might have been born on the other side of the Milky Way. This mixing is what makes the Milky Way a chemically homogeneous galaxy. The enrichment from supernovae is spread out like a drop of dye in a stirring cup of water. It ensures that the ingredients for life, carbon, oxygen, iron, are available everywhere, not just in the pockets where they were made. The churn is the circulation system of the galactic organism. As we look at HD 186302 in the constellation of the Peacock, we are looking at a survivor. Like the Sun, it survived the chaotic dissolution of the cluster. It survived the perilous journey through the spiral arms. It avoided getting too close to a supernova or a black hole. It has burned steadily for 4.5 billion years, keeping its own counsel in the dark. There is a grandeur in this survival. The universe is a dangerous place, filled with radiation and gravitational disruptions. For two stars from the same family to both survive to middle age, and to both be stable enough to potentially host life, is a testament to the resilience of G-type stars. We are the Goldilocks stars of the galaxy, not too big to explode, not too volatile to flare, but just right for the long haul. The map of the solar family is still mostly blank. We have found 2 or 3 likely candidates out of 1,000, but the hunt has only just begun. With each new generation of telescopes, our vision sharpens. We are building a family tree, star by star. And with each new cousin we identify, the Sun becomes a little less lonely. We realize that our isolation is geographical, not genealogical. We are part of a diaspora, spread across the spiral arms, but forever linked by the light of our shared beginning. We have found the lost kin. We have identified the stars that share our bloodline, the solar twins like HD 186302 that mirror our Sun in almost every measurable way. They are the same age, the same size, and made of the same primordial ash. But a star is merely a furnace. It is the hearth, not the home. The true mystery lies not in the nuclear fire of the Sibling, but in the dark, cool spaces orbiting around it. We are driven by a singular, haunting question. If the Sun has a twin, does the Earth have a twin? The discovery of the solar siblings provides astronomers with the most perfect laboratory nature could possibly design. In the chaotic hunt for extraterrestrial life, variables are the enemy. When we compare the Earth to a planet orbiting a red dwarf, or a massive blue star, or a star that is billions of years older or younger, we are comparing apples to oranges. The variables are too numerous. But with a solar sibling, the variables are controlled. The star is the same. The starting materials are the same. The time elapsed is the same. If we look at these stars and find silence, it tells us one thing. If we find life, it tells us everything. To date, our search for planets around the identified solar siblings has been tentative. We have scanned them for the subtle wobbles caused by massive gas giants, the hot Jupiters, and found little. This absence is paradoxically good news. A solar system dominated by a hot Jupiter is often a chaotic place where small, rocky worlds like Earth are ejected or swallowed. The lack of giant monsters suggests that the systems around our siblings might be calm. They might be arranged like our own, giant planets on the outside, protecting rocky planets on the inside. We are looking for the Goldilocks zone, the habitable zone. This is the narrow ring of space around a star where the temperature is just right for liquid water to exist on the surface of a planet. Not too hot, where oceans boil into steam. Not too cold, where they freeze into ice. Because our siblings are G-type stars like the Sun, their habitable zones are located at the same distance, 1 astronomical unit. We know exactly where to look. We are looking for a world circling its star once every 365 days, bathed in the same golden light that falls on our own forests and oceans. But finding such a world requires technology that pushes the very limits of optics. Earth-sized planets are tiny and dim. To see one next to the glare of its parent star is like trying to see a firefly hovering next to a searchlight from 1,000 miles away. We use the transit method, waiting for the planet to cross in front of the star, blocking a tiny fraction of its light, or the radial velocity method, measuring the star's wobble. As we stare at HD 186302, we must consider the role of planetary architecture. Even if the star is a twin, the arrangement of the planets might be radically different. The solar system was shaped by the specific movements of Jupiter and Saturn. We believe Jupiter migrated inward early in our history, the grand tack, clearing out the inner solar system before moving back out. This violent, sweeping motion might have been the crucial event that allowed a small, wet Earth to form. Did HD 186302 have a grand tack? Did it have a Jupiter to act as a shepherd? If the answer is no, the sibling system might be crowded with super-Earths, planets larger than Earth but smaller than Neptune, orbiting very close to the star. This is the most common type of planetary system we see in the galaxy. Our solar system, with its neat separation of rocky inner planets and gas outer planets, is actually somewhat unusual. If our siblings have different architectures, it suggests that the formation of planets is highly chaotic, driven by random collisions and migrations, rather than the initial chemistry of the cloud. But let us imagine that we find it. Let us imagine that in the data from the upcoming Plato mission or the Habitable Worlds Observatory, we detect a signal, a planet the size of Earth, in the habitable zone, orbiting a star that is the Sun's genetic twin. The implications would be staggering. We would be looking at Earth 2.0 in the truest sense. A world made of the same stardust, baked for the same amount of time. This brings us back to the concept of Lithopanspermia, but with a new urgency. If life began in the birth cluster and spread between the systems via rocks, then this twin planet might not just be habitable. It might be inhabited by our distant cousins. Evolution on Earth took 4.5 billion years to produce intelligence. If the sibling planet started with the same microbial seed at the same time, has it followed a similar path? Or has it diverged? Perhaps the dinosaurs were never wiped out there. Perhaps the planet is covered in a global ocean with no continents. Perhaps it is a desert world. The experiment of the siblings allows us to replay the tape of life. If we find life there, and it uses DNA, and that DNA relies on the same amino acids as ours, it would be strong evidence for a shared origin in the nursery. We would know that we are part of a galactic biological family. But how do we detect life across 184 light years? We cannot see the creatures. We cannot catch their radio signals, unless they are technological. We look for biosignatures. We look at the atmosphere. As the planet passes in front of its star, the starlight filters through the rim of the planet's atmosphere. The gases in the air absorb specific colors of light. By analyzing this filtered light, we can determine what the air is made of. We are looking for a state of chemical disequilibrium. In a dead world, gases settle into a stable state. Carbon dioxide and nitrogen coexist happily. But on a living world, biology is constantly messing things up. Life produces waste gases that shouldn't be there. Oxygen is a prime example. Oxygen is highly reactive. It wants to bond with rocks. If you stopped all photosynthesis on Earth today, our atmospheric oxygen would disappear in a few million years. The fact that our atmosphere is 21% oxygen means that something, life, is constantly replenishing it. So, we look at the solar sibling. We search for the spectral fingerprint of oxygen, and methane, and ozone. If we find oxygen and methane together, gases that destroy each other unless constantly renewed, we have found a smoking gun. We have found a biosphere. Conversely, the silence of the siblings would be equally profound. If we survey all 1,000 siblings, once we find them, and we find dozens of Earth-like planets, but none of them have oxygen, none of them have life, it tells us something terrifying about our own existence. It tells us that the great filter is real. It means that the step from dead rock to living cell is incredibly difficult, so difficult that it happened only once in 1,000 tries, even with the perfect ingredients. It would mean that we are the lottery winners of the cluster, the only spark that caught fire. It would make the Earth infinitely more precious. We would be the sole custodians of the consciousness of our stellar family, the only eyes that opened to see the universe. There is also the question of time. The Sun and its siblings are middle-aged stars. They are halfway through their lives. This means that if life evolved on a sibling planet, it has had the same amount of time to develop technology as we have. If intelligent civilizations are common, a solar sibling is the most likely place to find one. They would be at the same technological level, or perhaps slightly ahead or behind. Imagine a civilization on a planet orbiting HD 162826. They look up at the night sky. They see a yellow star in their constellation of the Centaur, where the sun would appear from their perspective. They analyze its light. They realize it is a solar twin. Do they wonder if they have siblings? Are they pointing their radio telescopes at us right now, waiting for a signal from the lost family? The geometry of the galaxy means that we are slowly drifting past each other. The window for contact might be millions of years long, or it might be brief. We are ships passing in the galactic night, signaling with our spectra. The search for sibling planets is also a search for our own future. As G-type stars age, they slowly get brighter. In 1 billion years, the sun will be 10% brighter, likely boiling off Earth's oceans. By looking at siblings that are slightly older or slightly more evolved, we can see a preview of our own fate. We can see what happens to an Earth-like planet when the star begins to heat up. We are looking into a crystal ball. We are also looking for the failed Earths, planets that started like ours but went wrong. Venus like runaway greenhouses, Mars like frozen deserts. The solar siblings likely host a museum of planetary outcomes. By studying them, we learn how fragile our own paradise is. We learn exactly how narrow the path of survival truly is. The technology to see these worlds is on the horizon. The extremely large telescope, ELT, in Chile, the giant Magellan Telescope, and the future space observatories are being built with these specific targets in mind. The list of solar siblings provided by Gaia is the target list for the next 50 years of astronomy. We are moving from the era of hunting for stars to the era of hunting for worlds. There is a deep emotional resonance in looking for a twin Earth. It satisfies a primal human need, the need to not be alone. We project our own loneliness onto the cosmos. We want to believe that somewhere out there, under a familiar yellow sun, there are oceans like ours, forests like ours, and perhaps beings like us, wondering about their origins. The solar siblings offer the best hope for this connection. They are the family we were separated from at birth. And while we can never go back to the nursery, the molecular cloud is gone, dispersed by the winds of time. We can look across the void and recognize the resemblance. We can find the other children of the nebula. As we continue our journey through the story of the sun's lost family, we must accept that the answers will not come quickly. Detecting an atmosphere across light years requires patience. It requires staring at a faint dot for weeks, collecting photon after photon, teasing the signal from the noise. It is a vigil, a long, silent watch in the dark. But the vigil is worth it. For in the light of our siblings, we may find the reflection of ourselves. We may find that the story of life on Earth is not a solitary monologue, but part of a chorus that began 4.6 billion years ago in the cold, dark heart of a gas cloud. The family is scattered, yes, but the conversation may not be over. We have spent much of our journey looking for stars that resemble our own. We have hunted for the solar twins, the bright, yellow G-type stars like HD 186302 that mirror the sun's size and temperament. It is natural to look for one's likeness. We seek the reflection of our own face in the galactic crowd, but in doing so, we have inadvertently ignored the majority of the family. The laws of stellar formation are dictated by a power law known as the initial mass function. Nature prefers to make small things rather than big things. For every massive blue giant born in a molecular cloud, there are a handful of sun-like stars. But for every sun-like star, there are dozens of red dwarfs. These are the little sisters of the sun. They are small, often possessing only 10 or 20% of the sun's mass. They are cool, glowing with a dim, ruddy light that is barely visible against the black of space. And they are everywhere. Statistically, of the 1,000 siblings born in our nursery, perhaps 700 or 800 of them were red dwarfs. The search for the solar family is, in reality, a search for these faint ghosts. While we have found a few bright brothers, the vast majority of our kin are hiding in the shadows, overlooked and catalogued as anonymous specks of red light. Finding them is the greatest challenge in galactic archaeology, but they hold the greatest promise for the future of our lineage. The invisibility of the little sisters is a consequence of their frugality. A red dwarf burns its hydrogen fuel with extreme slowness. Because they are low mass, the pressure in their cores is just barely high enough to sustain fusion. They sip at their energy reserves while the sun gulps. This makes them incredibly dim. Proxima Centauri, the nearest star to Earth and a red dwarf, is invisible to the naked eye despite being right next door. To find a solar sibling that is a red dwarf, we cannot rely on the simple visual surveys of the past. We need infrared eyes. The upcoming missions, like the Nancy Grace Roman Space Telescope, are designed to peer into the dim red end of the spectrum. They will allow us to pierce the veil of obscurity and finally take a census of the smaller siblings. When we do find them, we will discover that they are the keepers of the deep time. The Sun is a middle-aged star. It is 4.6 billion years old, and it has perhaps another 5 billion years of life left before it swells into a red giant and dies, shedding its outer layers to become a white dwarf. In the grand scheme of the cosmos, the Sun is a transient phenomenon, a brief flare of yellow light. But the little sisters are practically immortal because they mix their fuel thoroughly, circulating the hydrogen from the surface down to the core. They can burn for trillions of years. Long after the Sun has died, long after the Earth has been vaporized or frozen, the red dwarf siblings will still be there. They will still be glowing with the same steady amber light they had when they were born in the cluster. This makes them the ultimate archivists of our history. The chemical fingerprint of the birth cloud, the specific ratio of iron to oxygen that defines our family, is locked inside them. They will carry this signature into the deep future, preserving the memory of the Sun's origin long after the Sun itself has erased it. If a future astronomer, 1 trillion years from now, wants to know where the solar family came from, they will not look at the dead husk of the Sun. They will look at the living little sisters. There is a profound comfort in this longevity. We worry about the end of the world, about the death of the star, but the family line will continue. The DNA of our nebula is safe. It is stored in hundreds of low-mass vaults, scattered across the galaxy, hardened against the passage of eons. But the little sisters are not just passive vaults. They are also hosts. We know that red dwarfs are prolific planet makers. The Kepler Space Telescope taught us that almost every red dwarf hosts at least one planet, and often many. These systems are tight, huddled close to the warmth of the small star. This raises a fascinating possibility for the future of humanity, or whatever we evolve into. In 5 billion years, the Sun will become uninhabitable. It will expand, scorching the Earth. We will need to leave. Where will we go? We could move to Mars or the moons of Jupiter, but eventually, the Sun will die completely. If we want a home that lasts, we must look to the stars. And what more poetic destination could there be than a sibling? Imagine a migration, not just across space, but back into the family. We identify a nearby red dwarf sibling, a little sister star. It is stable. It is young in terms of its lifespan. It has planets. We travel there. We settle on a world that is made of the same stardust as the Earth, orbiting a star that shared a crib with our Sun. It would be a homecoming, a return to the fold. We would be reuniting the intelligence that evolved around the yellow brother with the longevity of the red sister. In doing so, we would ensure the survival of our civilization for an eternity. The red dwarf epoch will last for 100 trillion years. It is a timescale of nearly infinite potential. But before we can dream of migration, we must understand the character of these siblings. Red dwarfs are temperamental in their youth. They are prone to violent flares, bursts of magnetic energy that can strip the atmosphere off a nearby planet. We need to know if our siblings are calm or chaotic. The chemical composition we share might play a role here. The amount of metals, heavy elements in a star, affects its magnetic activity. Because the solar family is relatively metal-rich, our red dwarf siblings might be calmer than the average M-dwarf. They might be Goldilocks dwarfs, small enough to live forever, but chemically heavy enough to be stable. Finding this out is a key part of the current research. The galactic churn continues to mix us. The siblings are not static points on a map. They are moving targets. Some of the little sisters have likely been flung far out into the galactic halo, traveling in lonely, high-arching orbits above the disk. Others might have plunged deep into the core. We are identifying streams of stars, groups that move together. By finding the stream of the solar family, we can predict where the siblings will be in the future. We can calculate the galactic reunion. There will be moments in the future, millions of years from now, when our orbit around the galaxy intersects with the orbit of a sibling. We will pass close to one another again, a close encounter. Imagine looking up at the sky in 10 million years. A red star is getting brighter. It is moving fast against the background field. It is a little sister, swinging by for a visit. For a few thousand years, it might be the brightest star in the sky, a red eye watching over the earth. And then it will recede again into the dark. These encounters are rare, but inevitable. The galaxy is a mixing bowl, and eventually, the ingredients brush past each other. As we gaze at the faint red stars in our telescopes, we are looking at the safety deposit boxes of the universe. The massive stars are the show-offs. They spend their currency quickly and spectacularly. But the red dwarfs are the savers. They hoard their hydrogen. They represent the long-term investment of the cosmos. The sun is a spendthrift. It is burning through its inheritance at a furious rate. But the little sisters are frugal. They remind us that survival is not about brightness. It is about efficiency. There is a humility in recognizing that the sun is not the protagonist of the family story. It is merely the most famous member. The true protagonists, the ones who will see the end of the story, are the ones we can barely see. The orphan narrative of the sun is therefore only a half-truth. We are orphans only in the sense that we are separated by distance, but in time we are outlasted. The sun will pass away, but the family will remain. Let us rest in the knowledge of this continuity. The universe is built on redundancy. Nature did not put all its hopes in one star. It made 1,000. It made some big, some small, some fast, some slow. It ensured that no matter what happens to the sun, the signature of our creation will survive. The little sisters are out there, burning their low flames. They are keeping the watch. They are the night lights of the galaxy. While the sun blazes and tires, they endure. The legacy is safe. You are part of a story that does not end with the sunset. It continues in the faint red glow of the eternal siblings. Sleep in the assurance of the deep time. Sleep in the care of the sisters. We have journeyed far. We began in the cold, chaotic nursery of the molecular cloud, where the sun was born alongside 1,000 brothers and sisters. We watched as the winds of the first supernova blew the nest apart, and we followed the family as they drifted into the lonely currents of the Milky Way. We have scanned the heavens with our modern eyes, hunting for the chemical fingerprints that reveal our lost kin, and we have found them, faint, distant sparks like HD 186302, holding the memory of our creation in their light. But every story has an ending, and the story of a star is no different. The isolation of the sun is not a permanent state. It is merely a long phase. As we look toward the deep future, the narrative shifts from one of separation to one of transformation. Tonight, in this final chapter, we will watch the sun complete its life cycle. We will see it shed its golden skin, returning its substance to the galaxy that birthed it. And we will discover that in the end, the orphan does not die alone. It joins a new family, a silent, eternal procession of ghosts drifting in the dark. To understand the fate of the family, we must look at the clock of the galaxy. The Milky Way rotates once every 230 million years. We call this a galactic year. The sun is currently about 20 galactic years old. It is a young adult in the prime of its life. But the galaxy will keep turning long after the sun has grown old. In about 5 billion years, the hydrogen fuel in the sun's core will run out. The hydrostatic equilibrium, the balance between gravity pulling in and energy pushing out, will break. The core will collapse, and the outer layers will swell. The sun will become a red giant. It will grow so large that it will swallow Mercury, Venus, and perhaps the Earth. It will become a monster, blazing with a fierce, unstable luminosity. This transformation will happen to all the siblings. The massive ones have already died. The solar twins, like HD 186302, will follow us into the red giant phase at roughly the same time. Across the galaxy, the family members will flare up in unison, like candles flickering before they go out. It will be a synchronized senescence. But the death of a low-mass star is not a violent explosion. It is a gentle release. As the sun shudders in its old age, it will puff its outer layers off into space. The atmosphere of the sun, rich with the hydrogen, helium, and carbon it has forged, will drift away. It will form a planetary nebula. Imagine a sphere of glowing gas, expanding slowly into the void. It will be beautiful, a colorful shroud of ionized gas, illuminated by the dying core in the center. This nebula will be the sun's final gift to the universe. And here lies the beautiful irony. The sun began in a nebula, and it ends as a nebula. The orphan returns to the state of its birth, but this time the gas is not pristine. It is enriched. The atoms that were once inside the sun, and perhaps the atoms that were once inside the Earth, will be mixed back into the interstellar medium. They will float into the spiral arms. And out there in the dark, they will mix with the nebulae of our siblings. The gas from the sun's death shroud will mingle with the gas from HD 186302's death shroud. The physical substance of the family, separated for 10 billion years, will finally touch again. From this mixed gas, new stars will be born, a third generation. These new stars will contain the atoms of the sun and its siblings. The family line does not end, it branches out. We become the ancestors, the grandparent stars of a future cluster. The DNA is reshuffled and passed on. But what of the core? When the nebula drifts away, what is left behind? A white dwarf. A tiny, dense sphere of carbon and oxygen, the size of the Earth, but with the mass of a star. It is a diamond in the rough, glowing with a fierce white-hot heat. This is the corpse of the sun. It has no fuel. It generates no new energy. It simply shines by the memory of its past heat. The solar siblings will all end up here. One by one, the G-type stars and the K-type stars will shed their skins and shrink down into these crystal spheres. The family of stars will become a family of white dwarfs. The red dwarfs, the little sisters, will take much longer. As we saw in the previous chapter, they will burn for trillions of years. But eventually, even they will run out of fuel. They will shrink and cool, joining their bigger brothers in the graveyard. This leads us to the degenerate era of the galaxy, a time far in the future when star formation has ceased. The lights have gone out. The Milky Way is no longer a bright spiral. It is a dark disk populated by the remnants of stars. In this dark era, the orbits of the siblings will continue. Gravity never sleeps. The white dwarf sun will continue to circle the galactic center. The white dwarf HD 1863002 will circle with it. But the galaxy will be changing. Without the gas to act as friction, the orbits will become more random. Encounters will happen. Over quadrillions of years, dead stars will pass close to one another. Imagine the sun, now a cold, dark black dwarf, a cooled-down white dwarf, drifting through the void. It passes another black dwarf. They do not see each other. They emit no light, but they feel each other. A gravitational tug. A nod in the dark. Pitch 1%. It might be a stranger, or it might be a sibling. In the infinite stretch of time, the family members will dance around each other again. The churn that separated them will eventually bring them back into proximity, if only for a fleeting moment in the eternal night. There is a profound peace in this ultimate fate. The anxiety of separation is a feature of the living universe, where time is short and distances are obstacles. But in the dead universe, time is infinite. The obstacles dissolve. The family is united in the shared experience of rest. We began this story by looking at the sun as a lonely tyrant. We end it by seeing the sun as a humble participant in a great cycle. It is not an orphan, it is a traveler. It left home to do a job, to incubate life, to sustain a planet, to witness the universe. And when that job is done, it returns to the fold. The atoms of your body are part of this cycle. The carbon in your cells will likely end up in the white dwarf sun. You will become part of the crystal monument that drifts forever. Or perhaps you will be part of the nebula that escapes. You might end up in a new star, looking up at a new sky, wondering about your origins. As you lie here tonight, in the gravity of the Earth, orbiting the sun, orbiting the galaxy, feel the connections. You are not isolated. You are part of a web that stretches across 100,000 light years and 10 billion years. The light that hits your window is the light of family. The gravity that holds you to the bed is the gravity of the star. The orphan has found its home. Let the concept of the solar family settle over you like a warm blanket. The 1,000 siblings are out there, keeping watch. The red dwarfs are burning their slow red candles. The yellow twins are shining their steady golden beams. They're all turning together on the great wheel of the Milky Way. The wheel turns slowly, round and round, carrying us through the dark. There is no rush. There is no destination. There's only the turning. Let your own mind turn with it. Slow down the spin of your thoughts. Match the speed of the galaxy. One revolution every 230 million years. That is the pace of peace, The sun is resting. The siblings are resting. The cloud has dispersed, but the connection remains. You are safe in the family of light. Drift in the gentle gravity. Sleep. Good night.